Hello students, welcome back. Previously we went through all the preparations necessary to define a function. First we went through the Cartesian product and relation, along with some example problems here and some graphical visualizations too. And then we defined domain and range of relations, and then went through some examples as well. Now let us define a function. A function is a special relation where each x in the domain is related to one and only one y in the range. That's a key concept, so let me highlight it in blue. And here's a formulation. There are many different ways to represent a function, but this time let's use the pair notation. And this blue phrase here corresponds to this. A bit too abstract, but let me walk you through this. X is related to y1, and also x is related to y2. Then y1 and y2 must be the same. So they cannot be related to two different y values. Consequently, one and only one y value. Make sense? So this formal expression down here and this a little bit less formal expression mean the same thing. The blue parts are the same. About the first line, that means capital F is a relation, is a subset of a Cartesian product, and of course it's not empty. If that relation is a function, then in order for that relation to be a function, you have to have this satisfied. Let's go through some example problems here. Okay, we have these three examples. F1. How about this relation? It's just a function. Dark roast $1, light roast $1, coffee mocha $3, cappuccino $3. Each coffee product here has one and only one price tag. Does it make sense? Yes, it's a function. Here, dark roast and light roast have the same price, and the coffee mocha, cappuccino cost the same. No problem there, as long as each food item you sell, food or whatever, each item you sell has one and only one price tag, you can run your business. No confusion there. How about the next example here? Cheese melt $1, nacho supreme $2, bacon double $3, Happy Meal $5. Again, each food item here has only one price tag, so it's okay. No confusion here. In this particular case, they all have different price tag. Here, coffee mocha and cappuccino costed the same, all different, but that's not really the essential thing for a function. As long as each item in the domain has one and only one assigned from the range, it's okay. But this is going to be a trouble. Standard oil change $30, high mileage $40, full synthetic $50, full synthetic $60. Which is right? Full synthetic 50 or 60? Which is right? We have a problem here. We have a confusion. So this one is not a function. And then you cannot run your business like this until you remove one of them. Okay, used to be 60, but we have a coupon now, so back down to 50. That's one way to handle it. Or maybe you can remove this. Okay, coupon expired, going back to 60. In any case, you have to have only one y-coordinate value, only one y value in the range. Another way to express the same thing is to use arrow expression instead of pair expression. As a matter of fact, the arrow expression and the pair expression, they mean the same thing. So here, x is related to y. Again, x is related to y, or x is being assigned to y, because this arrow notation is used only for function, and function is a relation. So you can use relation notation, but function is a little special, and this is for all relation. And then if you use the arrow notation, the blue phrase over there can be rewritten like this. F is being assigned to x1 and also x is being assigned to y2. let me go again. And f assigns x to y1 and f assigns x to y2, then y1 and y2 must be the same. So x is being assigned to y1, and also x is being assigned to y2, then y1 and y2 must be the same. They cannot be different. So consequently, we have one and only one y in the range. Here's an example of those arrow notation, and I took this from the textbook. Cheeseburger, McChicken, bacon double, and triple cheeseburger, Happy Meal, they all have unique price tag. And then cheeseburger and McChicken, they cost the same, only $1. Bacon double, $2, and triple and the Happy Meal, they're both $3, kind of like that. It's a function. Here's another example of function using the arrow notation, but this one is a little bit special because each item in the range is related to one and only one from the domain as well. Here, not like that. Each one in the domain is related to one and only one in the range. So anything here is assigned over there. So I can follow the arrow and go. But I cannot backtrace. From $1, which one is it? Cheeseburger or McChicken? We have a problem. In this case, we can backtrace the arrow, so it's a little bit more special, but still, they're both functions. This one down here, that's not a function. We have a problem. This 240 is being assigned to 12 and also 20, so you cannot follow the arrow here. It's impossible because we have a problem at 240. Now, if you remove this 240, knock it off from the domain, and then consider only these three, then it's a function. But for now, this is not a function. Or you can remove one of those values and remove one of the arrows. That's another way to turn it into a function, but for now it is not. Now the third expression here, this one is the one we are going to be using the most often. Y equals capital F of x, where the right-hand side is uniquely determined by x. And x must be selected, of course, from the domain. We say this capital F of x as the value of the function. So this is called the value. And value of function is equal to y coordinate. I think I'll have to repeat this maybe 100 times. Here in this course, and then again in trigonometry course, and then again in calculus course, maybe even more. Remember, function value is the y coordinate. If you remember that, then you can handle most of the graph problems okay. If you forget, then I'm sorry, there's no way out. Now we're going to talk about these graphs in sections 2, 3, and 4, and we'll have plenty of occasion to talk about that y coordinate being equal to the function value. For now, let's postpone that a little bit and do some algebraic exercise. Let's consider a function determined like this, a real function, because both domain and target are real numbers. And then f of x is 2x squared minus 3x. Okay, all right. From here, let's find the function value f of 3 and the function value f of negative 1 and also this quantity here. How do we do that? Okay, f of x is this. Okay, all right. And then you're going to substitute x equal to 3. Okay, all right. In place of x, I'm plugging in 3. So I substituted 3 in place of x in the left-hand side, so I have to do the same thing in the right-hand side as well. And then we can do your computation. 3 squared is 9, so 2 times 3 squared is 18, and minus 3 times 3, so we get 9. That was easy. If you know substitution, that's easy. If you don't, you can't. How about the next problem here? Same deal, except I'm substituting x equals to negative 1. So x is negative 1. So here I'm putting negative 1. And in place of x here, I'm putting negative 1 again. Any more x? No? Okay, substitution complete. And then let's do the computation. Negative 1 squared is positive 1. So this is 2 plus 3, and we have 5. How about this quantity here? Divided by let me expand the font a little bit. Okay, all right. The denominator is pretty simple. 3 minus some negative 1. That's easy. Now, what is f of 3? You calculated already. That's 9. What is f of negative 1? We have it here. That's 5. So this is the same as 9 minus 5 over 3 plus 1. So we have 4 over 4. We have this kind of computation. It's easy if you know how to substitute. Substituting gives you the function value, another substitution, and still more substitution. How about the next problem here? Again, this is a substitution problem. I want f of negative x, right? So I'm going to substitute negative x in place of each x. And there you go, substitution complete. And we can simplify. Negative x squared is just x squared. So 2x squared, negative, negative, positive. And that's the answer. Now, what about the next part here? I'm looking for negative of f of x, right? And f of x is actually 2x squared minus 3x. So the substitution yields this. So in place of f of x, I can substitute 2x squared minus 3x. And we get negative 2x squared plus 3x. So in general, these two are different. I can simply put negative outside. As you can see, these two are different. Sometimes you're lucky and they're the same, but most of the time, in general, they're different. In any case, it's another substitution. So you can substitute inside the parentheses in place of each x, or you can substitute entire f of x equal to something. Whenever you have an equality, you can substitute. Okay, one more to go. How about this? Oh, this is a little bit beyond the scope of what I have in my mind. Okay, let's talk about it. Let me expand the font a little bit further. Okay. Now, what is f of x? That is 2x squared minus 3x, as we have over here. Doesn't make sense. So this one here, which I just highlighted in green, is this one. No problem there. Now this one, that's going to take a little bit more effort. So I'm substituting x plus h in place of x in the definition here. So that's the definition here. I just copied and pasted. Let's put some space in between. And we want x plus h. So in place of x, I need x plus h. Same here. I need x plus h. So this one I just highlighted in red. It's becoming that. After that, breaking up all those parentheses and taking the like terms together and simplifying all the way like this, the detail is left to the students. The substitution part we went through, I think that'll be helpful.